Okay?
Explain that.
Percentage error?
Say it again.
Is that calculating as percentage?
Not percentage error, actual error, which will affect the percentage error as well. But I'm saying, just in terms of actual error. What is error? What's actual error? The distance between what? Actual and approximate, right? Actual minus approximate, the absolute value. That's what it always is. So in our case, it's the distance between what? F of A minus our little expression here. Oh, sorry, not F of A. F of X and L of X. Right? Where the order you put those in there doesn't really matter because you're going to take the absolute value of that difference. Okay, but that's our error. That's our actual error. So if F double prime, I'll say A. So if the concavity at A is large, then error increases. And vice versa, right? If the second derivative at our location is small, then error decreases.
Now, when you say the concavity is large or small, do you mean like the actual curve itself is
That's correct.
long,
So
or is it like
this
how
is
sharp the curve is?
It's how sharp it's turning. That's exactly right. That's exactly what the concavity is telling you. The number on the we talked about sine mostly last time. Sine of concavity, if the derivative is the second derivative is positive, okay, I know it opens up. The second derivative is negative, I know it opens down. We didn't talk much about the value of the number you're getting. So the larger the value of the number, if f double prime is 16, then that means that this is kind of folding on itself rather quickly. And so it's going to move further away from that particular tangent line more quickly as you get further away from A. And so your approximation will be worse.
Okay.
But if it is fairly, I don't know, flat, it's not turning as quickly, like the curvature is not as intense, so then it will lay flatter around our location, and your approximate will be a good approximate.
So if the concavity is small, it's more flat, and if it's large, it's sharper?
That's right. That's exactly right. Exactly right. And the absolute value here is just to tell you we don't really care about the sign in this case, right? Right.
Well, we just take, instead of finding approximation language, it's just by drawing out a tangent line. Dot.
Say it one more time. From which dot? Sort of here?
Let's say it's a dot close towards the bottom of the curve.
Is a dot closer to the bottom of the curve?
Yeah.
Here?
Yeah, we'll just draw another tangent line there, and then we can just get an approximation for what that slope there, we can grade change. I mean, just instead of approximations, why don't we just draw new tangent lines to match up?
Where do you want the new tangent? So if we start with this tangent line,
No, I would say just draw a new tangent line wherever the point is at. You see what I mean?
where this point's at?
Yeah, like once you're drawing another tangent line there.
To do what? Well, I don't know what it is there. I don't know the slope there. I don't know the function value there.
You know that the tangent line.
I know what?
I see. When you draw the tangent line, it's that you know what the slope of the tangent line will be. Or
So the idea is this is not really here. I don't know. I don't really know what's going on after my spot. In our application here, I don't really know that this curve is heading to this value. We're going to do problems where we do know, because the problems are trumped up Homer problems. We're saying in real life, what happens is you know something about the value of the function here, and you know something about its slope, and you'd like to have a guess as to what's going on later on in this function's life. But you don't really know that there's a blue curve here. You don't really know what's going on.
word problem. Is that what you're trying to say?
Could be, yeah. We're saying in real life in a lab, whatever you're trying to, you have information. You have localized information, right? That's what this is. There's your local information. And you're trying to extrapolate something about something more global. You want to extrapolate something that's going on out here, right? That's what it means to extrapolate. To do something extra. Do some extrapolating, right? So we don't really know what's going on with the function out here, but I can tell you that as long as I believe the curve is smooth, then more than likely, this would be a good approximation. I can tell you something about the future, right? I can approximate the future, even though I don't know exactly what it is. Now, obviously, if you're taking all these things where you have actual minus approximate, well, hell yeah, I got the actual here. What do I need the approximate for, right? But that's the way these kind of trumped up problems work at first, just to get you used to the idea of error and all these things.
Okay.
Yeah.
So why is it the second derivative of f of a?
Why is it the second?
Yeah.
It is a concavity.
Oh,
So,
okay.
so the sharper the curve turns, right,
Yeah.
it gets rid of fold more quickly, right? Well,
Yeah.
very quickly. Take an example, right? We're like
Yeah.
that. Well, now look how bad the error is now, right? Oh, now I'm this far away from the actual value.
Okay.
So the sharper it turns, the worse your approximate is going to be, because your tangent line won't be as close to the curve if the curvature is sharp.
I just
That's all it's saying.
didn't connect that.
Yeah, there's a pile of symbols sitting there, and it says is large, and this, yeah, that's what it's trying to say.
Okay.
Okay, so you got the main ideas now. More curvature, that is, the concavity is more intense, then you're going to have a worse approximation. If it is a concave down situation, you'll have an over approximation. Concave up, you have an under approximation. Now let's do a problem. Hey, Raja, you won't like this one. Number 7. Now I have green. Harry, can you see the green? Really? As clear as the blue and red, or not quite as clear? You can see it. Okay. It's a whole new world now. I got green. 7. The function is 12 minus x squared. We are supposed to write the equation of the line that represents the linear approximation, so there's our formula, to the following function at the given point A. A is 2. So we're going to write our linear approximation. We're going to find L of x, given this particular function. Then we're going to approximate something. And here's where it gets stupid, because this is what I was telling Raja. Well, I have the whole function. I have 12 minus x squared. I can do this. No way to approximate at 2.1. I'll just plug in 2.1 and get the real answer, right? It doesn't make any sense. Why am I approximating? I get the real thing. I know how to square decimals, I'm not afraid. Right? Just the way the problems start out in life. Right? So it is. So to create a linear approximation, we need f of a. What's f of a? You should be able to eyeball it. You can see the green, right? Blue, 8. Who said 8? Everybody agree? 8? 12 minus 4, right? 8.
And you're plugging it in.
Plug it in that formula, yep. Just creating this formula, that's what they want. That's our linear approximation. That's question 1. Find linear approximation. Our linear approximator. So L of x equals 8 plus f prime at a. What's f prime? So negative 2, and instead of x, I'm going to put the a value, right? Are we okay so far?
Wait, can you like show
The
for the
steps?
first one that using the linear formula?
Our linear approximator?
Yeah.
Let's do it like this.
I just
We know the pieces we need. It's f of a. So f of a, I'll write the whole thing out. I don't want to confuse you. This is a simple topic. We don't need any confusion. 8. Now we need f prime. It's going to be negative 2x. We need really f prime at a. So that's going to be negative 2 times 2, which is negative 4. What else do we need? X minus a. That expression, x minus a, will simply be x minus 2. So x minus 2. There's all our pieces. We need to create L of x now. So L of x is 8 plus f prime at a, negative 4, times x minus a, x minus 2.